Next, de volgende spreker is...
Our next speaker, when I just spoke about young people, it's Robin Zevotek from Underwriters Laboratories, UL. He's been active as a fireman for quite a while. He is also a researcher at the Underwriters Laboratory in the greater Chicago area. And Robin will tell us about his experiences with fire engineering at his work.
Thank you. Good morning. I apologize. I am all that is standing between you and lunch, so we'll try and keep things on schedule. I've been informed that schedule is very important, so we'll stick to that. First of all, thank you very much. It's a huge honor to be able to come out here and present to you guys on the research that guys and girls in the fire service and in the research community on what we're doing at UL. I have a great opportunity to work with a wonderful company. How many people here have heard of Underwriters Laboratories? Excellent. That's what we like to see. So how many of you have heard of it because it's on the sponsorship of the sign over here? So Underwriters Laboratories started off as a testing company. They were out there to make sure that there were safe products in the world. So when electricity first started in the US, there was a large challenge with fires. They weren't exactly sure why these were occurring, so the company started. Our founder, William Merrill, went through and was looking at testing different products that were electrically made to determine how safe they were in fire. Fast forward to what we do today, and we span the whole gamut between electrical safety, environmental safety, materials safety, and in my world, firefighter safety. Interesting point of that is UL has a mission and a goal. In the US, or in general in the world, our goal is safer living and working environments. As was discussed earlier by Chief DeCrane, the working environment of the firefighter just happens to be the living environment of the citizens in your country. That's a great partnership for us at the Firefighter Safety Research Institute because we have an opportunity to impact both the living environments of the citizens along with the working environments of the firefighters all at the same time. To do that, we've done a significant amount of research on fire service tactics and some of the technological challenges of the fire service. This is just a list of them as we go through. If you're interested in any of those topics, obviously I cannot hit them all today, but our website does a very good job of addressing those and giving you the information you're looking for. The ones in red are the topics we're going to cover today, or at least portions of those projects. As we start discussing them, you'll understand why it's very difficult to go over the entire project as we walk through. So first thing I want to talk about is the traditional learning process for the fire department. In the US, we have standard operating guidelines which typically involve strategies and tactics for how to handle a specific situation on a fire. They're generalized so that you can kind of adapt them to the specific incident because fires are never the same. And when you join the fire service, you're handed a book. They tell you to learn those. Hopefully you learn those before you start training on them, and you go out and you practice these different tactics and strategies, and you apply them on incidents. When you apply them on incidents, you gain some experience. That experience hopefully translates back to your ability to continue to apply that on incidents. In some areas they critique, in some areas they revise those and go back into and adjust the standard operating guidelines. One of the things that the Firefighter Safety Research Institute really thinks that there's missing here is a part that exists in many other disciplines throughout the world, and that's research. Because without good information on what develops these strategies and tactics, can we really effectively have good strategies and tactics? So our thought is if we can add a research component to this entire process of firefighter training, now we can give the correct information and take some of the value of that experience and learn where those questions exist. For the firefighters in the room, I'm sure you've been to a fire and something happened and you couldn't explain it. So what do you do about that? Well, in the US Fire Service, we call that an anomaly. We can call that an extreme fire behavior. If you're in the New York City Fire Department, it's known as a fireball. Whenever there was anything they couldn't explain, it was a ball of fire, and that's what happened. We can take that information now and study those particular incidents and try and look for the physics that goes on and the fire dynamics that was going on and get the principles to the firefighters so that they can then apply those on incidents. So it's taking that experience, it's testing it under fire research, getting it back into the strategy and tactics so that they can now train their firefighters on that. We take a lot of strides in my country not to tell firefighters how to do their job, but to educate them on what's really happening. So that's a lot about what we're going to talk today. Hopefully we can go through and address a few things. The three that I've chosen to talk about all work around ventilation. So ventilation, depending on what fire department in the U.S. you're talking about, has different meanings and different practices and tactics. About 7 years ago now, we were awarded a grant to study how that ventilation affects residential structures, specifically how it affects residential structures with today's modern fuels. When these fire service tactics were developed, the fuel was very different. As Chief DeCrane pointed out, he had two side-by-side videos. One went to flashover in 30 minutes, and one went to flashover in about 3 minutes. About 10 times difference in the growth of that particular fire. So in 2010, we studied what happens when you open a door and a window on a house, and what does that do to the fire behavior. 2008. In 2010, we moved that to a U.S. Fire Service tactic of vertical ventilation. So climbing up on the roof, making a hole in the roof, and theoretically letting all of the hot smoke and gases out the top of the structure. We took a look at that. Followed on that, naturally, was the third process of ventilation that the firefighters are taught in the U.S. of positive pressure ventilation or using fans to affect the flows within the structure. So what we're going to do today is I'm going to give a very quick overview of what the experiments look like, and then we're going to talk about what we develop as tactical considerations from this research. And these tactical considerations actually come from individuals that we bring in for each specific project, along with our advisory board members who kind of have a holistic view of the type of research we're doing. They are all firefighters. They serve in different ranks from in our country, from all the way from lieutenant or firefighter all the way up to chief officer and chief of department. There are many reasons we do ventilation in the fire service, and there's many reasons we think we need to do ventilation in the fire service. And when you start thinking about the topic, one of the best things you can do is go back to the firefighter training manuals to try and pick those out, those reasons why firefighters are doing ventilation. So what I did is I took a look at a couple of textbooks that are used in the U.S. to teach firefighters, and I looked at what are the different reasons that we ventilate. And some of the main reasons that stick out in almost every single one of them is we want to improve the interior atmosphere, we want to lower the temperature, and we want to make it easier for firefighters to get in there and effect rescues and extinguish fire, along with making it easier or longer duration of survivability for a potential occupant. That seems consistent regardless what type of ventilation you're trying to use. So in 2008, we studied this in single-family residential homes in the U.S. We had 2 room scale burns. We did 3 heat release rate burns, which is trying to characterize the amount of energy in furniture that exists. And then we did another 15 experiments in our single-story structure and our 2-story structure. The single-story structure was about 1,200 square foot. It was designed to mimic construction in the U.S. in the late 50s, early 60s time. And then a 2-story structure, which was almost 3 times as large, had an open floor plan where you could see from the front to the back of the house, and all rooms open to that center area. We did 7 experiments in the single-story and 8 in the 2-story. I could go one by one and show you all the different experiments, but rather than do that, let's look at some of the tactics that we developed coming from those. So one of the biggest things that was identified in that particular project was the understanding of how fire grows and spreads within a structure. If you go to the traditional fire, or any of those textbooks that I referenced before, they showed a curve that showed you how fire developed. And in the US, you memorized 5 stages of fire growth. You had the ignition, the incipient stage, the growth stage, the fully developed stage, and the decay stage. And those were your 5 stages. You memorized them. You wrote them on all the answers to the textbooks. When the chief or the captain or lieutenant asked you, you were able to regurgitate them. But your understanding of them may not have quite fallen in line with how actual fire grows and spreads within a structure. So that's where we came up with our new fire behavior curve for that educational purposes. When you have a fire in a structure, it starts out at ignition. So an object becomes ignited. If there's enough energy being released from that object, it can grow and spread to other objects, and you're in a growth stage of the fire. You're limited by how much fuel is available to burn, how close are other objects to the object that's burning. After a certain period of time, though, due to the nature of how energy is released in these products that burn and the products that are in our houses, we enter a growth stage that is now ventilation limited, because fire burns in direct proportion to the amount of oxygen available. If the house or structure is closed, the oxygen slowly is burned out of the room and is no longer there. Eventually, you hit a point in this growth that there's not enough oxygen to sustain combustion within that compartment. Typically, we find this to be somewhere to between 14 to 15% oxygen concentration within the fire compartment itself. At that point, you'll reach a decay stage. The fire doesn't have enough oxygen. It can't burn anymore. Because it can't burn, it can't heat up other objects in the room. They cannot burn, and the fire just slowly starts decreasing in energy. What's it waiting for? Well, there's several options. There could be, the fire could fail a window in that structure, allow air to come in, and the fire could grow. In the United States, the police officers could arrive on scene and decide that they want to see what's going on inside the structure, so they open the door. Or the fire department could show up and have smoke coming out of the structure, and they need to go in and figure out where that smoke's coming from and extinguish the fire. Any 3 of those options, or even just a citizen opening the door or leaving the door open, is going to add more air to that fire. When they add the air to that fire, it's going to enter another growth stage. That growth stage could be very, very rapid depending on where they make that opening and when they make that opening. Well, that opening is ventilation. So in our study, we realized that as we're going through and looking at firefighters trying to remove smoke from the building, they're missing the very important part that every time smoke leaves, oxygen comes in. And when the oxygen comes in, the fire grows. It may reach flashover in that stage, but one of the most important parts that happens is, regardless of how many openings you make in that structure, it still hits a point where it's ventilation limited. The only way to take that fire from a ventilation limited state, needing more oxygen, to a fuel limited state where it won't burn quite as much fuel, is to apply water to it. You could remove the entire roof of that structure, and because of the way air is entrained to the base of a fire, the outside walls would still prevent some oxygen from being entrained into the structure. So when you think of it that way, ventilation during a growing fire is not capable of actually reducing temperatures inside the structure. It's going to continue to increasing them. So one of the tactical considerations that I think stood out the most from this was that when you go through the front door as a firefighter to put the fire out, you need to think of that as ventilation, because ventilation adds air to the structure. And that front door getting open to go put the fire out is going to add air to the structure. Go on YouTube, you can find any amount of videos of this going on. You have some firefighters that have shown up to a fire. They're putting their protective equipment on, they've stretched a hose line, the front door is open, and within a matter of seconds, that oxygen reacts with the hot fuel that's inside the structure, it ignites, flames are over top of their head, and this guy realizes, well, I'm going to need the hose line to put it out, but he can't actually get back in there to get it. So, what can you do about that, correct? If you show up to a structure where there's smoke coming out of the structure, there's obviously something going on inside. You have several options. One of them is to do nothing. One of them is an exterior attack, and one of them is an interior attack. What I would advocate, regardless of which one of those you're going to choose, is to understand the ramifications of what you're doing. If you're going to open that front door, it is going to allow air into the structure. When you allow air in, the fire will grow. You will need to do something about that. One of the things we came up to do about that is to control that door. If you limit how far the door is open, you can limit the amount of oxygen that's entering the structure. If you limit the amount of oxygen that comes in, it gives you a little bit more time to find that fire before it reaches that flashover stage in that room and causes conditions that the firefighters and occupants can't survive. So let's look at a video of this. We didn't actually have two houses side by side. These are the same house in our lab, two separate videos. On the left, we opened the front door and closed it a little bit to limit the amount of oxygen in. On the right, we left it fully open. You can see the timer in the bottom right here is about 5 times real speed there. But you'll notice the fire on the left, just by looking at the volume of smoke exiting the structure, you can determine that there's much more smoke exiting here on the right than there was on the left. If conservation of mass holds, which means as much smoke comes out in mass needs to go in with something else to make it up, you can tell that you're adding much more oxygen to the fire on the right, or air, 21% oxygen, into the fire on the right than you are to the fire on the left. So that begs the question, well, if I have to do some sort of ventilation because there's someone in there, or my firefighters want to go in there, and I need to reduce temperatures, and I need to make things better, where can I do that where it's going to be effective for the occupants and the firefighters? So we did a whole bunch of experiments, and we looked at the difference between venting close to where the fire is, if the fire is in the living room, or far from the fire. And we have graphs of temperature which show that fire in the growth stage, it becomes ventilation limited and decreases. The front door is open and the window is ventilated, and we take a look at what happens. And the interesting part is, regardless of whether you make the opening close to the fire or far from the fire, the same thing happens. Oxygen enters the structure. It may provide a momentary decrease, and in momentary it can be 10 to 15 seconds is what we've seen. But within at least a minute to a minute and a half, you see a rapid rise in temperature that exceeds the ability of firefighters' protective clothing to protect them. It exceeds the ability of occupants to be inside that structure, and you're in a bad situation. Regardless of if it was far or near, you exceed temperatures of 1600 F. So we're well above the 600 F where we were trying to, well above the 150 C that we were trying to maintain for occupant tenability. The difference between far and near is how far the oxygen has to travel to get to the fire, not the effect of letting more smoke out or letting more oxygen in. So in the far occurrence, the oxygen has to travel, the air has to travel in the window and all the way back to the base of the fire. When it's doing that, it's mixing with the smoke that's in the structure, and it's slowly decreasing the amount of oxygen that's in it. And you can see that in the temperatures. It doesn't quite get as hot as when you made the opening near the fire. In our fire service training manuals, there's a lot of discussion about whether you should make a ventilation opening high in the structure for the roof or a high window, or you should do it low. So we did tests to look at that, if we open the upper window or we open the lower window. And what you'll notice is, when we open the upper window, things got worse much quicker. Well, that makes sense to me because I barbecue on a grill a lot. Every now and then I like charcoal grill. I like the smoky taste of it there, even though it might have some PAHs in it. And I know to get my grill going better, I have to take the top off and let air in through the vents on the bottom. If I close the vents on the bottom, the grill doesn't burn efficiently. Well, essentially, that's what we're doing here. You're opening high with a door coming in low, and whether it's a fireplace or a barbecue grill, you are doing the exact same thing of making the most efficient, effective fire growth that you possibly can. Whereas if you open low, you're allowing less air in, and the fire takes a little longer to grow, but it still grows to the same point. Which leads us which begs the question, does ventilation really do anything for you on the fire ground? And in conclusion, if you would like to take a look at all of it, we basically determined that Until you put water on the fire, ventilation is a very hazardous activity. But as soon as water gets to the base of the fire, everything changes and flips. And as much ventilation as you can provide, the faster that environment will return to its original or ambient conditions. One of the other things that we took a look at in this study was a concept of vent, enter, isolate, search, which in the US means if you have a fire and you want to go into that fire to find a victim, you have a couple of options on how to get there. You can go through the front door, or you can go through a window to get into that structure. If you choose to go in through the window, luckily we know the presentation, if you choose to go in through the window, you have a very excellent opportunity to make the environment inside that room better. How do we do that? You can isolate the door that goes into another room. So if you happen to find a bedroom and you open the window or ventilate the window and see that there's a bed in there, most likely there is a door somewhere in that room that you can close. If you can close that door, and the presentation was on the screen, you would notice that the amount of the temperature within that room would decrease because you're taking the flow from in that structure back to you're taking the flow that was coming from the fire through that bedroom and out the window, and you're shutting it off and you're not allowing it to occur, along with decreasing the amount of oxygen that's allowed to come into there. So it makes it much more tenable in that room, and it can last much longer. Do we have any idea why we'll continue. So from there, instead of studying just horizontal, we wanted to look at vertical ventilation, because in the U.S. Fire Service, that's something that's used probably two-thirds of the fire service. So to look at vertical ventilation, we built the same structures that we built in horizontal ventilation. We started the fires in the same spot to allow us to compare the two fires to each other, and it allowed us to look at the different tactics of ventilation. Now in the U.S., we have a standard hole size that you need to cut in the roof of a structure to make it effective to ventilate, or so we thought. So that standard hole size is 4 feet by 4 feet. Closer. Nope, still not up there. So the 4 foot by 4 foot hole. In some instances, that didn't seem to be effective, and most firefighters said, well, that's obviously because your hole was too small. Bigger is always better. So why don't we create a hole twice the size, a 4 foot by 8 foot hole? And if we go ahead and create that 4 by 8 foot hole, I can skip ahead. Thank you. So if we go ahead and create that 4 by 8 foot hole, what's going to happen? So here's our two structures again. On the left, we're going to open a 4 by 4 hole. On the right, we're going to open a 4 by 8 hole. And we start a fire in the living room, and we try and see what happens. So we simulate our firefighters coming in and making an opening. We give them a little bit of time to put a ladder up, to get to the roof, to start making their hole. And after a little bit of time, we'll ventilate the roof structure. We ventilate them both at the same temperature to make sure that the fire growth was fairly consistent. And take a look at the two front doors as that ventilation occurs. Now this fire is showing a little more flame, but you'll notice you still have a pretty decent exchange. Once you start making openings in the roof, what we know is the neutral plane, where the gases are exiting high and coming in low, begins to rise up a little bit. When that rises up, more oxygen enters the structure. As the oxygen enters in, it increases the fire size and the fire grows. So although for a momentary amount of time, you've allowed all the smoke to go out the top of the structure, as it grows again, it starts to come out the front door more, and we're stuck to the same situation regardless of which hole was created. And it's in a matter of 10 to 15 seconds was the difference. So twice as much hole didn't really do a whole lot for you. So here's the temperatures inside the living room when we made a 4 by 4 hole. Much like we talked about with venting a low or high window, when you make an opening high in the structure, you're creating the ideal exhaust conditions. And as soon as that opening is made, the fire rapidly increases in temperature to flashover conditions, and you've made the space in there untenable. If we make a bigger hole, the exact same thing happens. It doesn't matter how big the hole we make is on the roof, we are still creating the same conditions, and the fire just continues to grow. So then, if you are going to choose this tactic, because as I said in the beginning of the presentation, I'm not out here to tell you how to fight a fire. I'm here to help you understand what's going to happen if you do. So if you're going to choose this tactic, it's all about the flow that you're creating on how effective that tactic is. So if I have a fire in the living room and I open the front door and make a hole in the roof, I'm creating that perfect chimney. It's the fireplace, right? Not quite going well enough, just open that damper up, allow as much air in as you possibly can, that fire will take right off. Same thing works within a structure. Flip that, and this is what the fire service was taught for a very long time in the US, that you want to do this type of ventilation. So what if we flip that, and if the fire's in the bedroom, instead of making that opening perfectly over top of the fire, like you're trained to let all the fire out and create that perfect chimney, let's make it not over the fire. Let's make it in another room. Well, now it's all about how air flows. Instead of increasing the fire size, the air, which you're letting in the structure through the front door, has to travel all the way through the living room and back into the bedroom, has to mix with whatever the reaction that's going on in there. It may increase the fire size slightly, but then all of those smoke products have to exit that door. Then they'll travel back down the hallway and out through the roof vent. Because that roof vent is also limited by the door can't let enough smoke into the living room, and you can let more smoke out of the living room than the door is pumping into the living room, and conditions will get better in the living room. Contrary to that, conditions in the bedroom will get worse because you're adding more oxygen to it. And if there happens to be a bedroom across the hall which is open, conditions will also get worse in there as the fire begins to try and spread across the hall. So it's about understanding the different types. Again, as I said earlier, we put water on either one of those, things get better. So in the U.S. Fire Service, they like to ask us to test everything, because if the principle exists in a single-story house, it obviously is not the same for a two-story house. So we go ahead and do the same experiment in a two-story house. And in this one, I have some pictures that help illustrate that. When we make the opening directly above the fire, it doesn't increase visibility. We don't see anything. It's too thick, dark smoke to see. When we make the opening away from the fire, that door is restricting how much smoke can come out of that room, and that smoke is exiting through the top hole, and it improves visibility in the hallway. So it's all about understanding the flows that are created to be able to understand how effective or not effective your ventilation is going to be. So then we'll go one further. We talked about opening doors and windows. We talked about opening roofs. Let's talk about using high-powered ventilators, because if you make a hole in the structure low and you make an exhaust high and that's not a big enough fire, if you blow a lot of air through that front door, it'll increase the fire even more. It'll make it easier to put it out, trust me. I'm joking. So positive pressure ventilation or positive pressure attack. I've defined them two different ways because it really doesn't exist in literature right now, but positive pressure attack is using the fan before you put water on the fire. Positive pressure ventilation is using the fan to remove products of combustion from the house after you put water on the fire. We had the same setup where we're doing experiments in a single-story and a two-story house. We opened these experiments up to over 500 visitors. We had some as far from the Netherlands that were willing to come out and watch some of these experiments. It yielded 72 hours of video, 2 million data points, and 750 graphs. So as you can imagine, I'm still going through some of that information to try and determine what all of it means. But we can take a look at some of the concepts that were in all of them and discuss how that affects things. We invited all of the manufacturers of the current ventilators in the fire service to participate. They all sent in fans, a total of 6 of them. We tested 2 of their fans, 1 gas and 1 electric for each. So let's take a look at what happens when we're using a fan without fire, because that's what we have to understand, what happens with the fan without fire before we can add the fire and complicate things. Well, we tested all 5 fan manufacturers that we had submitted in our single-story structure with a couple of different flow paths. And what we realized was if we take a look at the average of all the fans, we were somewhere right around about 11,000 CFM for our fan flow. But some fans could create more pressure than other fans. When we do that in the two-story structure, we're right about 12,000 CFM of airflow, no matter what fan we're using. So that begs the question, what's limiting this? Why are they the same? One structure's 3 times the size of the other. You should see some differences. And what it turns out is ventilation is very proportional to how big the opening is. And because our opening was the same size here as it was here, we could only remove that amount of products of combustion from, or that amount of air from the structure. Another thing we're taught with fans is how close to the structure are they? The further back from the structure, the less air it's capable of moving, right? Or so that was thought. As we tested a fan by putting it between 3 feet, I'm sorry this is hard to read up there, but between 3 feet and 15 feet from the entrance door. At 3 feet from the entrance door, it flowed 3,000 CFM through our opening. If we moved it all the way back to 15 feet, it still flowed 3,000 CFM through our ventilation opening. It's kind of interesting. Why would that occur? So let's look at the flows at the doorway itself. That's what this graph is. It's showing us the different air velocities as it's entering that front door. And we'll look and we notice that at some elevations, mainly the top area, we have air flowing out of the structure, whereas on the lower half, or on the bottom half of the door, we have air flowing into the structure. Well, what's happening is these fans are so powerful that they're actually overpressurizing the structure. And because it can't put a uniform pressure on the front of the structure, some of it has to go somewhere. Physics says that if there's a high pressure in one place and a low pressure in the other, that whatever your medium is going to flow from high to low. Well, if the living room pressure is much higher than the outside pressure is, it's going to come back out the door. It's not going to effectively stay inside. So what we need to do is be able to take the fire that's in there when we start adding fire to this and move it such that all of the fire products of combustion that are being created are moved away from the fan, away from the crew approaching the fire, and exhausting it out the window. Well, we did a couple of experiments trying to look at how big does that window need to be. Because there is all kinds of different theories about how big the window needed to be. Some said it needed to be equal to the size of the door. Some said it was 2 times the size of the door. Some said it was 5 times the size of the door. That's a pretty big variation. Our doors were roughly about 20 square feet, and our windows were just under that. So our windows were slightly smaller than that. And when we started without any fire, we started our fan up and we took a look at the pressure inside the structure. As we talked before, pressure is going to flow from high to low. When we had one window opening, if we take a look at the red line here, that's the pressure in this back bedroom where we're trying to flow all the air through. And we notice that that has the lowest pressure within the structure. So some air is going to flow into that bedroom and out the window, and it's pretty conservative. When we make 2 openings in there, so we make it so that it's larger than 1-to-1 for the opening, we notice that it takes the pressure in that back bedroom and drops it down to essentially what the pressure is outside. Well, that's ideal for us because the larger the difference in the pressure from this bedroom to the hallway and living room, the more the air is going to flow into that bedroom. When that pressure is up near the pressure of the living room, the whole house acts as one pressure volume, and it doesn't really move as much air. There's not that constant flow through. And we see that in our temperatures and our velocities when we add that second opening. So this is the velocity with the fire, and we're looking at the green and red lines. There are the top of the door, and the other 3 are the bottom of the door. We allow the fire to grow, and it allows smoke to come out the top of the door. We turn our fan on, and it pushes all the smoke into the structure. But with it, it pushes extra air into the structure. As it pushes air in, the fire grows, and it starts to create enough pressure to come back towards the fan. It takes this pressure in here when there was no fire and makes it up close to the level of the rest of the structure. When we make that second opening, we drop it down, and all our flow starts to exit out of that doorway of the structure just like we expect it to. And we notice that with the temperatures. If we're looking at the temperatures in this hallway, which is the green, the 4 lines here, green line being the top, we see that the temperature was going up just outside that door. It's going up because there's still some heat that's able to flow out the top of the door. When we make that second opening, which is this 4th line on the graph, you see that it drops the temperature drastically in that location. It dropped it because it allowed all of the clean air or cooler air that's in the living room to now flow to the area of low pressure, which is that back bedroom. So instead of thinking of this in terms of the door to the structure where you're putting in air and the window where you're exhausting air, it started to dawn on us that the more important point is actually the door to the room that's on fire. You don't need to create more pressure in the entire house than there is outside to ensure that all of the products of combustion flow out the windows. You need to create more pressure in the house except for the fire room to ensure that all of it flows out the window. So the only way you can do that is making an opening that's larger than the opening to the doorway to that room. If it's the same size, it's going to have the same amount of flow and you're not going to be increasing the pressure. Well, it was thought in the U.S. Fire Service that you could do this, and there was unidirectional flow at that door. At the top of that front door, there would always be flow into the structure. And you could use that flow that's going into the structure to tell you how well your ventilation is doing. If smoke comes out the top of that door, then your ventilation is not effective, and you need to make another opening. These are graphs of all of the experiments we ran in the structure, both structures. The black line is the doorway. If the line is to the left of the door, it means air is flowing in. If the line is to the right of the door on both sides, it means that air is flowing out. No matter what we did, there was air flowing out a portion of that door. Well, that makes sense because our fan is putting pressure into that living room. It increases the pressure in that living room. At some point, it's greater than one of the portions on that door. Once it becomes greater, it flows back out. That decreases the pressure in that room, and then it can flow back in. So understanding that difference is what's going to help you with understanding how the flow works. What we really need to look at instead of the front door is the front door and the exhaust point. As we start the fan here, you'll notice the front door will still have smoke coming out of it, whereas instead of having air going in and smoke coming out, this exhaust point now has complete exhaust throughout the structure. By evaluating the two of them, we can see how effective that ventilation is. If we're looking at just one point on the structure, we can't really tell how effective our exhaust is being in the structure. So what did we learn from all of that? We learned that flows inside structures are very complex, and there's going to be a lot more work looking at those. We learned that fans create additional flow that can adversely affect the conditions inside. Most importantly, we learned that at the front door, you don't get unidirectional flow. So if you're standing there waiting for that at the front door to make your attack onto the fire, that may not be the best indicator. And understanding how that flow is created is really the most essential part to that positive outcome. So with that, we'll talk quickly about some of the other things we have going on at UL. One of the main things is we do online training courses in addition to all of the research that we do. So for every research project, we write a report. That report gets upwards of 800 pages or something, depending on that. So if you want to go to sleep at night, that's a great report to read. In addition to that, we have a fire service report where we pull out all the important information for the fire service and we put it in a 50-page report. Now, 50 pages is a lot for firefighters to read. Sean doesn't make it through 50 pages, no way. Had to get my dig in, he did it to me. So we take that and we put it into an interactive online training course. And you can go to our website for free and take all of the training courses based on the research that we've done. So some of the very small topics that I covered today in 40 minutes by saying, hi, my name is Robin and I do fire research, you can look at all of these different topics on our website. In addition to that, we have a blog that we update with how progress on our particular projects are going. We co-sponsor a website with the Firefighter Close Calls folks from the United States, trying to look at the modern fire dynamics in structures, where we put up a lot of articles and they also put up some of the great work that's going on throughout the country. If you want to follow us on social media, we have a Facebook and Twitter. We try and update those daily. And with that, if anyone has any questions, they can feel free to contact me. That number goes directly to my desk. You don't have to go through all the different UL's numbers. And if your question is, when will the positive pressure ventilation report be done? It helps if you ask me that every week so that I'm more motivated to complete it. Or so most think.
Thank you.
With that, does anyone have any questions? Hang on a second for the microphone.
Waar was het? Hier, middenin. Dat kan moeilijk zwieren.
Hello. What's the impact of this story on smoke ventilation systems? Because they are propagated by American and English firefighter and investigation people. Yeah, could you give us an answer?
That's an excellent question. We really need the codes to catch up, as Sean was talking about, Chief DeCrane, catch up with our modern fuels. Those smoke exhaust systems are mainly based on a design fire, as Susan talked about the other day. And those design fires are based on fuels that were manufactured 15 or 20 years ago. Because once you burn one couch, you don't need to burn multiple couches. You know how the couch burns, and if the couch didn't change, there's no need to do it. Well, even though the couch changed, we still haven't burned the new ones. So our codes really need to kind of catch up with that. As far as mechanical smoke exhaust systems, where you have an atrium and you're trying to exhaust smoke out of the atrium, that's based on a design fire. So if the engineer picks the correct design fire, they are capable of removing the products of combustion from there enough to allow people to evacuate the structure, not necessarily to allow it to never have smoke in the structure at all. When it comes to natural smoke vents in large warehouses, in that instance, it really is that occurrence of the fire is just going to get so large that it's going to overwhelm those smoke vents very quickly. And they may not be effective. But again, the codes still need to catch up to get there. So.
Links, rechts, vooraan. Ziet.
We call it positive pressure ventilation, but I think it's kind of a strange name because you're only creating an airflow in a certain direction. And you didn't mention anything about how the fan outside was flowing the air into in what angle and what distance from the front door, for instance. I think that makes a difference. That matters.
So that was one of the slides there. I talked about how far the fan is back from the opening, and regardless of where we move that fan, we only made a difference of about 5,000 CFM, which is only a difference of about 15% of the total flow of the fan. So you could change the flow by about 15% by moving it from 3 feet to 15 feet. By changing the angle, it did absolutely nothing to allow that flow to increase or decrease. So one of the takeaways that I'm still working through now is how do you control that fan? Because obviously one fan is not sized for every window in the world. So if we have to match our exhaust to that fan flow, how do we control it? If we can't move it back and we can't tilt it to do that, we may be able to adjust the throttle on the fan to be able to match those. But what indicators are you looking for at the different openings to tell you that you've achieved the correct flow in the structure? Because without the correct flow, you certainly can make things go bad very quickly.
But still, some fans, you showed a slide with some fans creating much more pressure than other fans, and then you said, well, that makes hardly any difference at all in the efficiency of the fans. But what pressure do you mean then? That's not a static pressure, I think.
That's the pressure so it creates a high pressure inside the structure. But that flow is not necessarily always going through the structure. Some of it is coming back out the front door. And that coming back out the front door is what made the flows fairly constant for all the fans, regardless of which fan we used. Even though it created more pressure, it was just coming back out the door rather than flowing through the rest of the house.
Yeah, because you have an opening in the separation construction. So but you mean the pressure inside compared to the pressure outside?
Yes.
That's what you mean, the static pressure. Okay.
Yep, static pressure.
Okay.
Well, thank you very much. It has been a great honor to come here and present and meet every single one of you. Wonderful hosts. I echo both Chief DeCrane and myself have had a wonderful time while we're here. We really hope we can come back to visit. Thank you.
Oké. Ja, dat is zo. Mag je nog even blijven, Robin, ook.
Just stay a moment. At some point I was thinking, oh God, I've got to be the referee between the two, because only at the very last they started kicking each other. Anyway, looking forward to the replay.
In de namiddag komt...
In the afternoon he'll be back. So once he's refueled, I'm sure he will go into the aspects of ventilation in even more detail. So Robin will be giving a second presentation this afternoon. We have Lieve and Hans. I know. Wait a second, I haven't forgotten. Lieve and Hans are going to discuss, and as Robin said, there are lots and lots of graphs, and the results from the different studies are going to be used. Zatvan version 2 will be discussed, and Ruth will also give an introduction class in the framework of your training program. That is, if I've understood it correctly. And after that, there'll be a break. So I have asked that you sort out your badges before the break, so that afterwards at 1:30 you end up attending the right workshop. And then there's something that Ricardo and Renee asked. They asked for just a moment to say something. I'd like to give you the floor. This is a comment off mic. The interpreters can't hear what's being said.
So as you know, that we try to gain a lot of knowledge, and we do the same as UL. And I think that Robin gave a very good example of that. But we also want to share the knowledge. That's why we do the streaming today. That's why we share the knowledge that we have today with all colleagues in the all over the countries, but also in other countries. And that's why also we think it's very important that all our reports and all our results and everything we gain and knowledge, that it is published in English, so that we can share it with everybody all over the world, maybe, at least if they speak English, but most of them will do that. And we cooperate with UL already for a few years, amongst other things, for this conference. We do the conference together. You also help us a little bit with the finances. And otherwise we would not, of course, without UL we would not be able to do this on our own. And I think that there is a lot of things that you cannot do on your own, and we have to cooperate within Europe, but also with other parties. So, and this special moment is because we had the report from the experiments in Zutphen. You know the experiments. They were all over the news. Of course, we had a Dutch report, and with a little bit help of UL again, we were able to translate this report into English. So now everybody all over the world can have the knowledge that we gained in Zutphen. And because UL helped us with that, we wanted to give the first English book to Robin as a representative of UL. Thank you very much for your help. And I know that he is going to read it very, very carefully, because maybe he's going to find some things that he can use in his own experiment. And
Thank you very much. It's really true that as the fire service throughout the world, as I get to travel and meet different firefighters, we all have very similar problems. And one of the main problems is financial. We can't all afford to do all the research. So if we can collaborate on all the different research projects and allow all the firefighters throughout the world to be able to benefit from our research, it's a great partnership that we can establish. So thank you so much for the first English copy. It will get read before I get back to the US, and hopefully we can use that going forward. Thank you.
Okay. And of course, a photo.
Don't stand before UL. Don't catch UL. Okay, perfect. Thank you.
And second thing that we are very great of, it's a big pleasure for us to have Chris here, because Chris is a representative of the fire service of Belgium or Flanders?
Flanders.
Flanders.
Not Belgium. That was a...
and in that way, he is an example
This is
of our...
confidential, yeah.
And in that way, he's an example of our cooperation, growing cooperation with the Flanders Fire Service. And we hope that that cooperation can grow further, maybe next year or year after next year, that we can have real cooperation also in research and knowledge exchange. And that is why Hans also wants to say something to Chris, I think, or not. Because we didn't prepare, he has the book. So
Yes. Chris, we spoke on the Congress in Kortrijk a few weeks ago already. It was established that our Flemish colleagues were very interested in our results. For that, we want to present you the second example of the report. And also because, of course, you are also the chairman of the FEU, the Federation of European Chiefs. Thank you very much.
Okay. Yeah. Thanks a lot. So maybe a small word, it will not only, and we had some big ideas already yesterday, it will be not only in the Flemish, let's say, connection. I will do my very best and my support to spread it all over Europe by means of the FEU. This will be done in the months that come. We won't wait for 1 year. Thank you.
So maybe it will not take that long before our dream comes true.
That's it, correct.
And I have to say, René reminded me that it is now available on the internet in English and in Dutch. And that's for our friends in Minsk and Zeeland.
Okay.